Well, good morning, everybody. We're going to try something a little bit different here today so you guys can see my smiling face. Um, what we're going to look at today is taking a look at things that are not mutually exclusive. So, if we follow along with the notes right here, let's just start off with a you try. Go ahead, figure out what the probability of getting a 6 or a 3 is. And I know you guys are watching videos from Miss Presley and Mr. Winiger. I like to talk about probability as desired over total. So if we look at getting a 6 or a 3, you got two possible things that you desire out of 8. So we get a 2 out of 8 probability, which simplifies to 1 out of 4. So if we look at the next one, what's the probability of getting a card that is either an ace or a king? So if we look at our deck of cards, which I got here, and I pull out all my aces and my kings. Let's find them. Got one ace. Should have 4 aces, 4 kings in here. There we go. So with that, we have a total of 4 aces, 4 kings, and gives us a grand total of 8 possibilities to out of our 52 cards. Same thing is the case for the next one where we're looking at a 4 or 6, 4 fours, 4 sixes, 8 out of 52 as well. So we get down into this thing where we're talking about things that are not mutually exclusive. So if we think about mutually exclusive, they cannot happen at the same time. So perfect example of mutually exclusive, flipping a coin and getting heads and tails at the same time. There's no coin out there, and I know you're going to sit there and say, well, it lands on its side. I get heads and tails. No, we can't flip a coin and get heads and tails at the same time. So those are mutually exclusive. Another example would be taking one card out of a deck and having it be both a 4 and a 5. It's impossible. They cannot happen at the same time. So when we look at things that are not mutually exclusive or overlapping, so we've got not mutually exclusive, otherwise known as overlapping. The example that they give us, or they want us to take a look at, is a situation where we pull a card out of a deck, and what is the chances of getting a king or a heart? Okay, so we know we have 13 hearts in a deck of cards, and we have 4 kings. But we also have 1 king of hearts. So what I don't want to do is count both the king and the heart that is also the king twice, because that will distort our probability. So when we look at this, we've got to add up our two things, all right, our 13 hearts and our 4 kings, and we've got to subtract away the 1 king of heart. So we've got a total of our 52, but we got our 13 plus 4 minus 1, which would give us 16 out of 52. So if I were to pull out all my hearts out of my deck of cards here, and also pull out all my kings as well, as you can see, I have 4 kings. All right. One of them being the king of hearts. I have 12 hearts here. All right. King of hearts is not in here because it's over here with these other guys. So altogether, I have a grand total of 16 out of 52. So when we talk about events that are not mutually exclusive, You see this formula down there at the bottom. So these are things that are overlapping. The formula that's given to us is probability of A or B is equal to the probability of A plus the probability of B minus our probability of A and B. Remember our notation. That is for and, that is for or. So in this case, if probability of A was our kings, that would be 4 out of 52. Probability of B was the hearts, 13 out of 52. The one overlapping one gets us a total of 16 over 52. That's the key thing. We got to remember to subtract away the thing that overlaps. And I'll come up with some other examples and put those in play for you guys as well. But if we look at the examples that they have here in the notes, turn it over to the next page, we've got a situation where you've got probability of A is 0.6, probability of B is 0.7, probability of A and B is 0.4. So I've got a 0.6 plus 0.7, subtract away the 0.4, and we get 0.9. So that's the probability of getting the or. Remember, this is equal to our probability of A or B. Example 2, traveling here back to Woodstock, probability that a person plays sports is 65%, probability that a person is between the ages of 12 and 18 is 40%, probability that a person plays sports and is in between 12 and 18 is 25. So what's the probability of a person playing sports or being between the age of 12 and 18? Once again, we got things that can happen in both. They can overlap. You can have a person that's between the ages of 12 and 18 that also plays sports. So what we get here is you have our probability of A. We'll make that the person between 12 and 18. So you have 0.4. Probability of B, which will make our people between 12 and 18, is 0.25. Or excuse me, I'm sorry. Let's redo that. Probability of the people that play sports was 0.65. Probability of the person between the ages of 12 and 18 is 0.4. The probability that they are between those ages and also play sports is 0.25. We're going to add these guys up, subtract away the overlapping piece, and we get a probability that they are between the ages of 12 and 18 or they play sports is 0.8, which is 8 out of 10. Treat this thing just like an algebra problem. We will give you 3 of these 4 things here. You will be missing 1. So if we look at the next situation, we're missing different pieces. We give you the or. The or is 0.2. We give you A. We give you B. But now we want to know what the and is. So we're just treating it like any other algebra problem that we've done before in the fact that we're missing one piece of information. So solving for this part, I get 0.75 minus the and is equal to 0.2. And subtract this over to both sides. Both sides are negative, so when I divide by -1, I get the probability of A and B equaling 2.55, 55%. Same thing with example number 4. We've got a situation where we give you A, we give you the or, and we give you the and, we're missing B. So I have A, I don't have this, that's my unknown. The and is 0.2, and my or is 0.8. So I get a 0.15 plus x, subtract that from both sides, and I get 0.65. So hopefully you guys are kind of following along, understand that it's just all we're doing is solving for a variable here. Key thing is mutually exclusive and not mutually exclusive. Understand the difference between those two. Mutually exclusive, they cannot happen at the same time. Not mutually exclusive, that's our overlapping. They can happen at the same time. We've got to subtract away the overlapping pieces. So if we look down example 5, you get a situation where you're looking at Miss Robinson's class, 12 boys, 16 girls. On Monday, 4 boys and 5 girls were wearing red shirts. So what is the probability of blue or red? Boy or red. So you have a total of 12 boys out of 28. You have a total of 9 people wearing red out of 28. We're looking for boys or red, so we've got to subtract away the and, the boys that do wear red shirts, which in this case was 4. And we get a total out of 17 out of 28. Second situation, probability of a girl or red. Got 16 girls. 9 were wearing red out of all students. The number of girls that were wearing red that day were 5. So we subtract that away, and we get 20 out of 28. So the last thing we got to look at today is the idea of a complement. And we talked about this before. Complement is the opposite of something happening. So the complement of flipping a coin and getting heads would be tails. Putting that in terms of a probability of getting heads is 1/2. The complement of that would also be 1/2. All right. Key thing with complements that we got to remember is those two things. The event and its complement will always add up to 1. So when we look at a complement, and we complement, our notation for that can be either A prime or A. We'll see above it. We'll see it both ways. So if we look at probability of the complement of A, it's going to be 1 minus the probability of A. So very easily, if I'm giving you that the probability of A is 0.73, then its complement is going to be 1 minus 0.73 or 0.27. Same thing, for example, 7, subtract the 0.42 from 1, and we get 0.58. So if we go back to Miss Robinson's class from above, and we look at just some basic ones with the complement, they're looking for what is the probability of it being a girl. So probability of being a girl from our previous situation was 16 out of 28. There's 16 girls. How about a probability for the complement of C, which would be not red shirt? So we had 9 people who had red shirts, total of 28, gives us 19 out of 28 that do not wear red shirts. Probability of a girl and not wearing a red shirt